1. Regression with time series data, stationary variable. Okay, for the last 2 weeks, we will study how to analyze time series data. What is a time series? It is data of the same unit collected over discrete interval times. For example, in our graph here, we have real GDP data, that's a time series. We can real GDP. Change of GDP is also a time series data. Inflation rate is a time series data, or change of inflation rate is a time series data. So let's say let t take integer values, t is index times, is a sequence of random variables. And one realization of this stochastic process, this is a sequence of random variables, then is the time series data that we observe. And we will be interested in the following quantities. First, what is the mean? The mean of yt, and bear in mind that this can depend on t. Okay, for example, let's say mt. So different times, y has the random variable y has different mean. Okay, maybe different variance. The variance is yt minus is mean, deviation from mean, squared, and take expected value. That's the second quantity. Third quantity is we call it covariance. It's a covariance between yt and ys. So is the expected value of yt, deviation of yt from its mean, times deviation of ys from its mean. And you know that if t is equal to s, then covariance of yt and ys is just, or yt is just become variance. Okay, no, this point. Covariance has a unit in it, so we can do some manipulation to get what is called correlation, or sometimes called autocorrelation, because it's correlation with itself, which is covariance, that's the covariance, divided by square root of variance, standard deviation of yt and standard deviation of ys. And this is called correlation between yt and ys. Measures the linear association, and these quantities can depend on t and s. Bear in mind. So this week we will focus on stationary and weakly dependent time series. What do we mean by stationary? Stationary means that the means and the variance, the mean of yt is the same across different periods. So which means expected value of y1 is equal to expected value of y2, so on and so forth. So this mean does not depend on time. Variance also does not change on time. The variance of y1 or yt more general is, we call it sigma y squares. Okay, so variance of y1 is the same as variance of y2, so on and so forth. So constant means and the constant variance. Thirdly, the correlation is decays. The correlation between two variables decrease as the further apart these two random variables are. So the correlation between yt and yt minus s depends on the time difference t minus s, which is s. The further the s, the bigger the s is, the smaller the rho it is. Okay, so this is called weakly dependent, or the dependence is weak. As s approach infinity, observations get further and further apart in time. They become almost independent. So this week we focus on analyzing time series which are stationary, which means constant means and variance, and the correlation decrease as the further apart in times. All right, in pictures, stationary variable look like this. Okay, so they roughly have the same mean variance, same means, same variance across times, and so a picture like this is stationary, and certainly we can actually conduct statistical tests to verify whether a time series is stationary or not. Time series look like this. It's not stationary. It's what we call slow turning wandering. Okay. Time series like this is also not stationary. It has a time trend in it. So we focus on this type of time series this week. Okay, we can test whether a time series is stationary or not, using, for example, like augmented Dickey flow test. We will talk more about this next week. So what can we do if a time series is not stationary? We can detrending, remove the trend components, and analyzing the remaining component, or difference the time series, analyzing the difference to data. Or sometimes say time series can expect seasonalities. For example, like monthly sales revenues, which might expect a peak around the Christmas times. Okay, that's sort of seasonalities. We can also remove these seasonalities, then analyzing the remaining component of the time series. For example, like this time series, airline passengers from 1949 to 1996. Well, we can see that there exists a time trend, upward time trend. Also, there seems to be kind of seasonality in it. Right, so we have a statistical process. We are interested in several quantities of it, like mean, variance, covariance, correlations. Using data or with one realization, many realization of this statistical process, we can actually compute or we have the sample counterparts of these theoretical quantities. For example, like mean, for a mean we have average, sample average, which is, you can view this as kind of sample version of the mean, theoretical means. Similarly, we can have a sample variance, and note that Okay, it is the deviation of yt from its mean squared, get rid of the negative sign, adding up, divided by t minus 1. Note that it's not divided by t, though in a large sample it does not make a big differences. But here we are divided by t minus 1 because we lose 1 degree of freedom in computing y bar. Okay. The covariance, and I hope you want to compare the formula of this with the theoretical versions. Okay. Covariance of yt minus 1, which is effective value of yt minus mean times yt minus 1 minus mean. Okay, very similar. I hope you agree. And similar, the S order sample autocorrelation. Okay, which is, bear in mind, pay attention to the index, the first index of the sum. It starts from S plus 1 because we are computing the S order sample autocorrelation. So we have to do some sort of observations because we are lagging the y by S period. Okay. It is often useful to test whether a sample autocorrelation is significantly different from 0 or not. For example, we want to construct models. We might want to understand this. We might want to have this piece of information. We run regression with time series data. We may want to check whether the error terms in an equation is serially autocorrelated or not. So we can do a hypothesis test. The null hypothesis is rho S. Remember, rho S is the S order autocorrelation. And bear in mind that we have the sample version is estimated rho S. Okay, we have this. We observe this. We don't observe this. Okay, so the null hypothesis is rho S is equal to 0. Alternative, rho S is not equal to 0, which means we are doing a two-tail test here. Be aware of this. Okay, we can show that under the null hypothesis, RS, which is a sample autocorrelation, or estimated version of rho S, has an approximate normal distribution with mean 0 and the variance 1 over t. So now a suitable test statistics is RS minus 0 under the null divided by the standard deviation. We get this, and it is normally distributed. Then at a 5% level of significance, alpha equal to 5%, then we can reject the null hypothesis. So we have this. If the sample value of our test statistics is bigger than 1.96 or smaller than 1.96, so this is 2.5%. 2.5%. Okay, that's how we can test the significance of autocorrelation. We can also use a diagrammatic representation for assessing the significance of autocorrelation. Sometimes we call this sample autocorrelation function or autocorrelograms. Like here there's an example of this. So we have the horizontal axis here is lag periods, and vertical is the sample correlation, sample autocorrelation. We can calculate the associate value and the associate 95% confidence interval, and we can see that for this particular time series, the autocorrelation is statistically significant at lag 1 to until roughly 18, lag 18, somewhere here. They're all statistically significant. Okay, we can use these correlograms to visualize this autocorrelation. Okay, this model of variables y to only depends on its past values. So we call this type of model auto-regressive model, like ARP, which has p lag. So yt depends on constant delta and theta 1 and its first period lag, second until p is period lag, and plus and error terms. Here delta is the constant intercept. Theta 1, theta 2, and theta p, they are the parameters, and delta and theta, they are parameters we can estimate from the data, the time series data we have. Okay, for example, in AR2 model, autoregressive of order 2 models for the unemployment rate time series, say ut is delta 0 plus theta 1 times ut minus 1 period lag, plus theta 2 plus times ut minus 2 period lag, plus error terms. And then we have data we can estimate delta, theta 1, theta 2. Okay, here is the time series plot for US quarterly unemployment rate from 1948 to 2016. Okay, that's the time series data we can visualize, then draw the graph. Okay, we can model this series using AR1 models, autoregressive of order 1 model, which means we will estimate a model of these forms. Ut is equal to delta plus theta 1 times ut minus 1 plus the error terms et. Or we can model this by an AR2 process or AR3 process. Okay. And now you should be wondering, so basically AR1, AR2, AR3, they have different lag length. And now you should be wondering, what lag length should we choose in practice? Okay, so this is about lag selection. We can choose the lag length to minimize the archaic information criteria. Okay, that's one statistics that we can look at. We will illustrate this by choosing lag length to be 2 or in estimated in AR2 models. So here to properly estimate these models, the key assumption is that conditional on IT minus 1, which includes is 1 year's lag, 1 period lag, 2 period lag, so on and so forth, expected value of ET is equal to 0. So this is exogeneity requirements of the error terms. So the OL estimation results look like this. Given our assumption, we can just use the ordinary least square estimators. We can also use it. We can also estimate this model using other estimation methods, for example, like maximum likelihood. they estimate different, the MLE estimation and the OLS estimation might expect small differences here. So here our OLS says that okay, UT is equal to 0.28852 plus 1.61282 times UT minus 1 minus 0.66209 times UT minus 2. And these are the corresponding standard errors. Okay, let's fit. So when we, remember we estimate this delta hat plus theta 1 hat UT minus 1 plus theta hat 2 UT minus 2. So we know this, we have data of this, we can calculate the fitted value. Okay, then this graph exhibits the original time series, which is in black solid curve, and then we can also draw the predicted value, fitted value. It is in dashed red curve, and from this graph we can see that the fitting is actually quite good. Okay, the fitted curve follows the time series closely. Okay, the time series itself closely. Right, after estimating the AR2 model, so now we want to utilize this model primarily for forecasting. Okay, so the latest data of unemployment rate is 2016 Q1, which is 4.9%, and the previous quarter, which 2015 Q4, 5%. Now let's forecast what is the predicted unemployment rate in 2016 Q2. So we want to predict this one. So we have estimate of the intercept, so which is delta hat. Estimate of this one, we know this. We have data of this. We know this. We have estimate of theta 2. We know this. Then we plug everything in here. So it's 0.28852 plus 1.61282 times 4.9 minus 0.66209 times 5. We get 4.8809. So the forecast of 2016 Q2 unemployment rate is 4.8809%. And you know that this forecast is kind of point prediction. Okay, it's not interval. This is our forecast, and we shouldn't be surprised that this forecast is going to contain errors. Okay, we haven't accounted for this fact yet. Okay, so that's the forecast of 2016 Q2 unemployment rate. Okay, let's do Q3. Okay, this is Q3. So the unemployment rate of 2016 Q3, again, we do it delta hat plus theta hat times 2016 Q2. But now you remember, be aware, pay attention to the fact that we haven't reached 2016 Q2, so we don't exactly know what's the unemployment rate then yet. So, but we have a forecast here. So let's use this forecast. And since, okay, bear in mind that we are plugging the predicted 2016 Q2 unemployment rate here, plus theta 2 hat times the unemployment rate of 2016 Q1. So we plug in all the numbers, do the computation, we get 4.9163%. And now I hope you appreciate that one important point here is that, okay, so we are using the forecast of, when we are forecasting 2016 Q3, we are using the forecast of 2016 Q2. So now 2016 Q2, it contains forecasting errors. So this fit, we are bringing in this 2016 Q2 forecasting error into the 2016 Q3. So the further away into the future we want to forecast, the bigger error we are going to make. The more, because of this accumulation of errors. Okay, so I hope this makes sense to you. Right. So not surprisingly, forecasts contains errors. So this work out these errors. So one period forecast, the actual value ut-1, which is unobserved for us at time t, big T. So remember our sample contains t is equal to 1 until big T, and we are standing at big T here today. That's today. Big T is today. So we don't know what's the unemployment rate in t plus 1, but we know that it depends on delta plus theta 1 plus ut plus ut-1 plus n error terms. Okay. So we have a forecast of this. So we plug in our estimate of these parameters delta and theta into the equation and ignore the error terms. Anyway, we don't observe it. So the forecast error will be this. We call this F1. Will be the actual value, the difference between actual value and the forecast value. And we are going to plug in this equation into here, this equation into here, then we get this one. Okay, so forecast error comes from several components. First is the difference in the true intercept and the estimated intercept. And the second parameter, third parameter, and the error terms of ET plus 1. So here typically we will ignore the errors from estimating the coefficients. Okay, so let's ignore this. You can think that we have sufficiently large sample size, so that the difference is very, very small, so we ignore it. Typically, error comes from ET plus 1. So the one period forecast error is ET plus 1. And bear in mind that this is random variables. Okay. Now let's compute the 2 period forecast. So the true value of 2 period, T plus 2 unemployment. And note that this includes an error terms ET plus 2. Our forecast. Okay, and now we're going to pretend that we are using, in practice we use delta hat and theta hat and theta 2 hat in the computation, but let's assume that this delta hat and delta are the difference is very, very small. We have sufficiently large sample size to make it small, so we can just write it as delta theta 1 and theta 2. And bear in mind, the only pay attention to these terms here, you hat. So this is the forecast of the previous period. Okay, so the error, forecast error, 2 period forecast error, is the actual value, the difference between actual value and the forecast values. And plugging this one in here, and this one here, then we can see that it consists of 2 components. First, the forecast error from the one period forecast error. Secondly, the second period error terms. So basically, comes from these two parts. And we know that F1 is equal to ET plus 1, so plug into here, we get this forecast, 2-period forecast error. And again, it's a random variable. Similarly, we can work out the 3-period forecast error. And I hope you appreciate that. The further we get into the future, the more errors we are having. We're having more errors in a sense. Okay, remember, 2 periods, 1 period, F1 is just ET plus 1, right? 2 period, we have ET plus 2 and ET plus 1. 3 period, we have ET plus 1, ET plus 2, and ET plus 3. Okay, and which makes sense, right? Because we are the further into the future, we want to predict, the more uncertain we are. Okay, so note that our assumption, exogeneity of error terms and homoscedasticities, then we can compute the variance of this forecast error. The forecast error, they are random variables. We can calculate the variance. For example, 1 period forecast errors variance is sigma squared. 2 periods is this. 3 periods is this. And again, it increases. It becomes bigger and bigger. And then we can estimate. We can estimate sigma squares. We can estimate the theta. We have estimate theta 1, theta 2. So we can plug in this estimate. So we get an estimate of this variance. Square root. Take a square root of them. We get standard errors. So get an estimate. So this we estimate the AR models are particular residuals, square them and get an average, get this sigma heft estimate, sigma squares, and that's the 1 period estimated 1 period forecast error. The variance is variance. Similarly for 2 period, 3 periods. Then we can compute the forecast interval. Okay, the lower bound is our forecast. For example, 1 period forecast would be y hat big T plus 1 minus T. Let's choose that. Let's choose alpha to be 5%. Okay, so it's 97%. T is our sample size. Minus 2, minus 1. This 2 comes from the lag length because we are doing estimating AR2. If it's AR3, it's 3. AR1 is 1. Minus 1, this one comes from the intercept, the constant. And there's minus 2. This minus 2, it comes from the fact that when we are estimating this sigma square, we lose 2 degrees of freedom because we have 2 parameters here. Again, 2 parameters, so we gotta take away that. Okay, so that's the lower bound and that's the upper bound. Okay. Right, so here is the forecast. So this is the forecast. This is the real the time series up until 2016, and that's the forecast, point of forecast. This is 95% confidence intervals. Okay, let's AR2 models and how we can utilize AR2 models for the purpose of forecasting.